In this video, we're going to look at some properties that logarithms have that we're going to find useful as we move forward. There's three basic ones that I want to introduce to start with. The first one is the fact that if you take the log of 1, you always get 0, right? And this makes sense just from looking at this statement and saying, if I write this in exponential form, it would look like this. A to the 0 equals 1, right? And we know if we take a non-zero number raised to the 0 power, we get 1, right? So that makes a lot of sense. So whenever you see that, you can just automatically put 0. Also, if you are taking the log of a base that happens to match the base of an exponential expression inside the logarithm, then the two bases is kind of cancel in a way. It's kind of a not the best way to say it, but that's kind of what's happening there. Now, to kind of justify this to ourselves, here's what I'm going to do. I'm going to circle these in blue, and I'm going to circle this in red. And what I'm going to do is I'm going to rewrite this in exponential form. So the base of the logarithm becomes the base of the exponent. This blue x goes there, and that's going to be equal to whatever's inside the logarithm. But of course, because that is a to the x, okay, of course, that makes perfect sense. All right. And similarly, um, if if it's an exponential expression with a logarithm in the exponent like this, again, I'm going to circle this a and this x in blue, and I'll circle the exponent here in red, and I rewrite that in logarithmic form. So I'll have the log base a of x equals the red. Well, of course, that makes perfect sense as well. Okay, so we can feel free to use these three properties here whenever we see them. So when you see in part A, the log base 5 of 5 to the 7th, well, you can just write down 7 immediately, right? Knowing that the 5s kind of just cancel each other out in a way. One like part B, you should take a moment to rewrite it so that the base is showing, right? There's no base written. It really means there's a 10 there. And so we end up with um, just -4, right? Because the bases once again match. Here's one where it's helpful to rewrite the natural log as the log base e of 5. And then this is a lot like property 3. So the answer just has to be 5. Here, again, base is matching. So the answer must just be 742. All right, now there's two more properties that we're going to introduce here. The first one is called the power property of logarithms. And this one's a little odd. What it says is that if you have an exponential inside of the logarithm, and you don't have that matching of the base of the logarithm with the base of the exponent like we were just looking at, you can still take that exponent and bring it down front and multiply. Okay, so a little bit strange. But what we're going to do is a short proof of this so that you can see it in action. So um, what we're going to do is we're going to take the left side and we're going to write it and say that it's equal to x. And then I'm going to rewrite this in exponential form. Okay. And then I'm going to do something that, you probably haven't seen, certainly you haven't seen me do in this class, but I think it'll be believable since you know that there's such thing as fraction exponents. What I'm going to do is I'm going to raise both sides to the 1 over p. Okay. And because I know that my power rule for exponents says that I'm going to end up multiplying x and 1 over p, this becomes a to the x over p. And this over here becomes m to the p over p. And of course, p over p is just 1, right? So you have that. Now, if I put it back into back into logarithmic form, I end up with log base a of m is equal to x over p. And then if I multiply both sides of that equation by p, then I have x by itself again, but now it equals something different than it did at the beginning. So now p log base a of m is equal to x. All right, so there you go. X is equal to that, but x is also equal to that. So that must mean these two things are equal to one another. Okay. I'm going to kind of go a little out of order of the notes here. So skip with me to this set of examples so you can really see how this works. So in part A, log base 3 of x to the seventh, that property we just learned gives us permission to bring 7 down. So there's no longer an exponent with the x. In part B, if I recognize that 32 is really just 2 to the fifth power, then I guess there's two ways that I can do this. If I use property number 2, okay, property number 2 meaning this one here, okay. If I use that property, then since the bases match, I could just immediately say the answer is 5. But using this new rule, I could bring the 5 down in front. And then, of course, because log base 2 of 2 is going to be 1, so I get 5 that way. So just two different ways for the same thing. Part C, log base 3 of, well, 1 million is the same as 10 to the sixth power, right? 1 followed by 6 zeros is 10 to the sixth. And here the bases don't match like they do in part B, so then I really do need that property if I want to um, write it without exponents inside the logarithm. Okay, so that's how that property works. Now, where it's going to really come in handy is in solving exponential equations that we'll do in the next video. But this is just a couple quick examples of how it can be used. All right, now backtracking to the second property I wanted to show you and give a little proof of. And this property has to do with the fact that we did discuss earlier that most calculators do not have um, a button that has log of any base you want. Most of them have two, natural log and common log, and that's it. So because of that, we want to use what's called the change of base formula. It gives us a way of calculating any logarithm, getting an approximation for it, um, when we don't have a button for that particular base of a logarithm. So what it says is that if you have log base a of m, then you can take any log you want of m and put it on top, and then that same log of a, which was the original base, and put it on bottom and divide. Now, because most calculators have the common log and the natural log, those are the two we tend to actually use in practice. Okay, so let me start before we prove this. Here's what this is saying. If you want to calculate log base 7 of 5, because there's no log base 7 button in my calculator, I can go ahead and do the natural log of 5 and divide it by the natural log of 7. So natural log of 5 divided by the natural log of 7. You can see it wanted me to round to 5 decimal places, right? So here's my 5, but after the 5 is a number greater than 5, so I'm going to bump that up to 0.82709. All right. And also note that the common log would have worked just as fine, right? Log 5 over log 7 gives you the exact same thing. So just changing that to log, exactly the same answer. All right. Now, um, the proof we did back here and the proof I'm about to do, let me just be very clear. That's not something I'm going to ask you to do on an assessment at any point. But I just do want to give you a justification for why this is true. So let's start by writing log base a of m. And let's, like we did in the last proof, let's set it equal to x. I'll rewrite it in exponential form. And then I'm going to take the log base b of both sides. Again, not something we've done yet, but I think is believable that if two sides are equal, then if you take the logarithm, the same logarithm of both sides, then they should still be equal. I can bring that x down in front through the power property. And then this might seem a little awkward, but the log base b of a is just a number, right? It's just a number. So go ahead and divide by it. So I can say, let's divide by log base b of a on both sides. And so you're left with x is equal to the log base b of m log base b of a. And so, of course, you have both sides of that equation both equaling x, so they must, in fact, equal one another.